Welcome back, everybody. In this video, we're going to talk about another very interesting function called the indicator function of the Cantor set. So first we have to describe what the Cantor set. The indicator function is not going to be the hard part of this. So the Cantor set, well, there's really sort of the first Cantor set that we'll talk about, and then down the line you can see, oh, there's actually lots of different Cantor sets that you can write down that are all kind of variations, clever generalizations of this, but this is good enough for our purposes. So we're going to start with the unit interval 0, 1, and I'm just going to refer to this set as C sub 0. Okay, so now the way the story goes is in the middle of the night, a group of bandits show up and they steal points from your set. So in the first night, they're going to show up, and when you wake up the next day, you notice that the middle third of your set is gone. So between 1/3 and 2/3 is gone. You still have 1/3 and 2/3 the points, but everything in between is gone. All right. And so we're going to label this set as C1. All right, so we notice, for example, we have two segments left. They're each of length 1/3. So originally, right, our length of C sub k, right, this length was 1, and now we're at 2/3. Okay, well, the next night, the bandits come back, and they take the middle third of each of your remaining intervals. Okay, and this is why we call them the middle third bandits. So they're leaving you with 2/3 of each of your intervals, but they're taking the middle ones. Whoops. Here's 2/3. This is 7/9, and this is 8/9. And you can see again, now our intervals that we have left over have length now 1/9. So in total we have, well, I could write it as 1, 2, 3, 4/9. But I'm going to write it in a slightly different way. I notice they've left 2/3 of what I had before. So 2/3 of 2/3 is 2/3 squared. All right. And then the next night, they're going to come again. All right. So, of course, it gets harder to draw this as we go. And they remove, these middle third bandits, they remove the middle third of each of my intervals. All right, so I'll just mention here right now, this is going to be 1/27th in length, okay, and I'm not going to write it everywhere. But again, you see they've removed 1/3 of everything you have, so they've left you with 2/3 of what you had, so the length of what you have left over is now 2/3 cubed, okay? And this is going to happen ad infinitum. We just keep on going forever and ever and ever. You keep on losing the middle third of each of your remaining intervals. Now, what is not at all obvious when you do this, right, is that you're going to get anything left over. But okay, you give it a little moment's thought, and you say, well, okay, since they're always removing the middle third, I guess I'm getting the endpoints for sure, right? Like they're never going to get rid of 0 because that's never going to be one of the middle thirds. So we know we get some stuff, but, well, how much stuff? Well, I guess if we always get the endpoints, and at each step along the way, we're creating more endpoints, right? So you can see here, right? Like originally we had 2 endpoints, and then we had 1, 2, 3, 4 endpoints, and then 1, 2, 3, 4, 5, 6. Oh my goodness, we get 8 endpoints, right? In fact, the number of intervals keeps doubling each time, so that is going to double the number of endpoints we get. I guess eventually, right, if we just kept on going forever and ever, we would end up getting an infinite number of endpoints. And so, hey, we actually know this set must be infinite. So that's kind of interesting. But it still doesn't seem like it could be too big of an infinite, right? Well, in fact, we're going to show it's actually an uncountably infinite set. So let me write down the precise definition we're going to give. So C, which is going to be the Cantor set, is actually what we get when we intersect all of these different C sub k's. Okay, now you'll notice, right, C1 is contained in C0, C2 is contained in C1, C3 is contained in C2, right? It keeps getting smaller each time. I want to do this infinitely, but I have no way of saying, oh, here's the last one, you're done. So instead, I just say, let's take the intersection of all of the CKs. All right, so the first thing I will claim is that this Cantor set, I'm going to write an M, this Cantor set, the cardinality is uncountably infinite. All right, and this is at first going to be a little bit surprising, but when you see how we do it, you say, oh, yep, that's the best we can. I mean, that's just going to happen that way. So let me first go in here and in C0, well, okay, you just I don't know, you just have this one interval. But once the middle third bandits come the first time, I break things up into 3 different pieces. So I'm going to label this in green. I'm going to label this first segment as 0. This middle segment, which is missing, as 1. And this last segment, we're going to label that as 2. All right, now I go into C2. Now everything down here has again been broken up. I have a 0th segment, a first segment, and a second segment, which they all came from the original 0th. So I'm going to label this as here as 0, 0. The one in the middle, I'll label this as 0, 1. So the first digit, right, that's referring to the original 0, okay? And then the next digit tells me what I'm currently in. And then this next one here will be 0, 2. In the middle, I could break this down. I don't really want to. I'm going to skip that. This would be, 1, 0, 1, 1, 1, 2, right? So 1, 0, 1, 1, 1, 2. But I don't really want to worry about that because those are not in my set, right? If they're, as soon as a point is out of some CK, then of course it won't be in any of the subsequent ones. All right, now I come down here and I'm in the 2 segment. So this will be 2, 0. This here will be 2, 1. This here will be 2, 2. All right, I go down to the next line, right? I'm in my C3 now, and I say, well, okay, this was the 0th segment, then there was zeros in the 0, 0 segment. So when I break this up, I get 0, 0, 0, where again, these first 2 zeros correspond to those 2 zeros. I'll skip this middle one here, and I'll just say, okay, now this would be 0, 0, 2. And over here, I would have 0, 2, 0, and 0, 2, 2, 2, 0, 0, 2, 0, 2, 2, 2, 0, and finally 2, 2, 2. And so what you might start to notice is that the points that I'm actually going to have potentially in my Cantor set only use the 0s and the 2s because I only use a 1 for something which occurs in the middle. And the middle third bandits are going to take all of those. What this means is that I can represent every element in the Cantor set by a string of 0s and 2s. All right, if I have a 0, this means I was on the left. If I have a 2, that means I moved to the right. But because this has to go on forever and ever, it must be some sort of infinite string of 0s and 2s. So what we can say there is that C has the same cardinality as the set of all sequences of the digits 0 and 2. All right, and what I claim is that this set is uncountably infinite. And we can prove this, for example, using Cantor's diagonalization argument. Okay, so let me give a name to this set. Okay, I'll just call it, I don't know, how about F? Why not? So assume F is countably infinite. Well, this means that there exists some bijection from the positive integers to f. So there exists a bijection, I don't know, how about we'll call it little g, from the positive integers to curly f. Okay, fine. That means that when I evaluate g on some positive integer, I end up getting some sequence in f. Okay, so for all positive integers little n, g of n is equal to some sequence, and how about I refer to the sequence as dn. So n is here telling me actually I'll put the n up top, right? So n is telling me what it's referring to, but then there's the first term in the sequence, there's the second term in the sequence, third term in the sequence, etc. Okay, so this is for d ln in the set 0, 2. Okay, so each one of these terms in the sequence is a number 0 or 2. Okay, fine. Now we're going to define a new sequence. Okay, how about I'll call this, I don't know, how about x dot? X dot is going to equal a sequence. It's going to be E1, E2, E3, etc. And how do I define these E's? Where I'm going to define the, how about say the lth term of this sequence to be, well, it's either going to be 0 or 2. That's good because I'm trying to build a sequence, which is in F. Now, when is it going to be 0? Well, what I'm going to do is I'm going to go to the lth sequence. So it means I'm looking at G of L. So it's going to look like DL1, DL2, DL3, etc. So I'm going to look at the lth sequence, and then I'm going to look at the lth term in that sequence. And if the lth term in that sequence is equal to 2, then E sub L will be 0. Okay, but then I could look at DLL and I could, well, what if it's not 2? Of course, that just means it's 0. Then I'm going to let EL actually equal 2. Okay, now, since F, or rather G, is surjective, okay, it's a bijection, so it is surjective. All right. There exists some little m such that G of m is equal to this x. Why? Well, because this x is an element of F, right? We've defined it in such a way that each of the terms is either 0 or 2. Fine. So I know that this little x has a preimage, m. Okay, but if that's the case, then this implies that dm1, dm2, dm3, etc., which is equal to G of m, is equal to x, which is equal to our E1, E2, E3, etc. Okay, so I have two sequences that are equal to each other, but if two sequences are equal to each other, they have to be the same term by term. Okay, well, why don't we look at, I don't know, how about say the mth term? So this implies that dmm has to equal em. Oops, down here. But this is a contradiction because we know that dmm and em are not the same because we have established up here that when you take some any L, E sub L is not equal to DLL. When DLL is 2, EL is something different. When DLL is not 2, EL is 2, right? Again, it's something different. So this is a contradiction. And where does the contradiction come from? It came from our assumption that F is countably infinite. Okay, so we conclude F is uncountably infinite. And hence, C, the Cantor set, is uncountably infinite. Hey, that's pretty good. So despite this set looking like it's going to be extremely sparse, we are able to show it is an uncountably infinite set. Fantastic. All right, next, let's get to the indicator function. So the indicator function on the Cantor set, this will be a function, well, we could define it on all of the real numbers. But what we're going to want later on is just on the interval 0, 1. So I'm just going to define it there. But again, we could extend this to all real numbers. Okay, the indicator function is going to be defined by just saying, well, if x is in the Cantor set, we return 1. If x is not in the Cantor set, we return 0. All right, so I would like to know some basic things about this set. For example, is it continuous anywhere, right? Okay, so let's see here. I claim that chi-c is discontinuous at all points in the Cantor set. So it is going to be discontinuous on an uncountably infinite set. All right, let's see why this is true. So first, let's let C be some element in the Cantor set and assume delta is some positive real number. So I know that I can find a power of a third. So there's going to exist some k such that 1/3 to the k is less than delta. Okay, I can make 1/3. I can raise it to a power. Every time I do, it's going to get smaller and smaller and smaller. Eventually, right, I'm getting less than delta. Fine. Now, what do we know about C? Well, C, recall, is the intersection of all of these CKs. And each one of these CKs is getting smaller and smaller and smaller. Yep. Fine. I also know that, well, if I'm in the Cantor set, then I must be in all of these CKs. And I mean, not just one of them, right? Like I'm in every single one of them. So I have this C, but this C must be, so thus, well, it's not really a thus because it's not coming from what we wrote above. So we have C is contained in, I'm going to say here, CK plus 1. Okay. Now in CK plus 1, how long are the subintervals? Okay. Well, we know the total length. We wrote that down here. But how about we put in length of subinterval? So in the first one, well, there's no real subintervals. They all have length 1. But here the lengths we said were 1/3. Here, next one, it was 1/9. But let me write that as 1/3 squared. Next one would be 1/27 or 1/3 cubed. So we see that the length for CK would be 1/3 to the K. So this tells me, right, in CK plus 1, so in CK plus 1, the length of a subinterval is 1/3 to the K plus 1. All right, so what if I start from this point C and I build a C coin of radius 1/3 to the K? All right, so this will be C minus 1/3 to the K, C plus 1/3 to the K. Well, if I build something this big, it will certainly be wider than an interval of length 1/3 to the K plus 1. Which means that this cannot be contained in any particular subinterval. Of course, if you aren't contained in one of these subintervals, you must contain stuff outside of the Cantor set. So this implies that this interval is not contained in the Cantor set. But if it's not contained, well, what if I replaced 1/3 to the K with the bigger radius delta? So this implies C minus delta, C plus delta is not contained in the Cantor set. Okay, but delta was arbitrary. This means I cannot write down any C coin that is contained in the Cantor set. So this implies that every C coin contains an element of the complement of the Cantor set. All right. So just as an aside, this immediately tells you, this implies that C is not an interior point of the Cantor set. In fact, C was arbitrary, right? So in fact, the interior points of the Cantor set, well, there aren't any. This is the empty set. So we would actually say C has empty interior. Okay, so we don't have so many examples of that so far, right? Functions that have no interior points. Okay, well, singleton sets, that sort of thing, but or discrete sets, that does it. So this is a more complicated version. Okay, but let's get back over here. So we said every C coin must contain an element of the complement. Okay, so if I write down any C coin and I apply the indicator function, okay, so let's say whatever this element was, let's say an element X of the complement. So this implies, well, if I apply the indicator function to, well, let's do it to C first, and then to X, well, when I apply it to C, I get 1. When I apply it to something in the complement, I get 0. And so the difference is 1. So in every C coin, I have points whose chi-C images are 1 apart. But that is going to contradict continuity. Continuity says if you want to get them really close, like, I don't know, let's say within 1/2 of each other, right? So if I wanted epsilon to be 1/2, then I should be able to get points close enough to C so that the F images, or in this case the chi-C images, are within 1/2. But we can't do that because any C coin I write down will have some X like this. So this implies that chi-C is discontinuous at C. Okay, and again, C was just chosen arbitrarily in the Cantor set. All right, so this proves chi-C discontinuous on the Cantor set. Well, what if I go outside the Cantor set? Well, this is our second claim then. Chi-C is continuous on the complement of the Cantor set. Now, this isn't as surprising because when we start looking at our intervals where you're outside the Cantor set, like there's just nothing there, right? Like you hold these big gaps, and the value is going to be definitely going to be 0 on all those gaps. Okay, so this actually is not as hard of an argument. It's mostly a topological argument. Okay, so first, when we removed the middle third, we were removing kind of this open bit. We were leaving 2 closed intervals. And so we have a union of closed intervals, and therefore, say C1, for example, is closed. When I keep removing stuff, I'm still leaving a finite number of intervals at each step. So what we get is that each CK is a finite union of closed intervals. And we know that if you take a finite union of closed sets, you again get a closed set. So this implies each CK is closed. Okay, but then the Cantor set itself is defined as the intersection of all the CKs. So C is, again, the intersection of all the CKs. These are all closed sets. And any intersection, right? We knew for finite unions of closed, we got closed, but for any intersection of closed sets, we again get a closed set. Okay, but if the Cantor set is closed, that then implies that the complement of the Cantor set is open. Okay, but now if the complement of the Cantor set is open, and I restrict my Cantor in the indicator function to the complement of the Cantor set. So let's do that. Restrict chi-c to the complement, right? So we're looking at chi-c now going from the complement to the real numbers. Okay, same function, only now we change the domain. All right. Now, what if I take the preimage of any open set in R? Okay, so the preimage of any open set in the real numbers. Well, if that open set does not contain 0, then you're not getting anything. Because what happens when we apply chi-c to C complement? I mean, we're not really getting all the real numbers here, are we, right? Because we know that chi-c of x equals 0 for all x in C complement, right? Like, this is actually the constant function. So if I don't get 0 out, then the preimage will be the empty set. So the preimage of any open set in R is the empty set. Or, well, what if 0 is in the open set? Well, the preimage of 0 is the entire complement of C. In either case, right, these are open sets. And so the preimage of any open set is an open set, and that is equivalent to chi-c being continuous. So this implies that chi-c is continuous on C complement. Okay, so that finishes the proof. So now we know the indicator function on the Cantor set is discontinuous on the Cantor set and continuous off the Cantor set. All right. We want to do more, though. We have all this wonderful integration theory. So yeah, maybe we should talk about, is this indicator function integrable? And amazingly, right, we're going to show that it is. Okay, so here's what we're going to do. I need a little bit of notation. So we've had these CKs up above. And let me now just write down some names for these subintervals. All right, so up here, for example, right, we had C1. I'm not going to relabel the 0 and the 1, but maybe I'll call this point, let's see, so since I'm in C1, I'll put a 1 here, and then this will be the first dot. And then over here, I have a C1, 2, and that's all I need. Here, I could do C2, 1, C2, 2, C2, 3, C2, 4, C2, 5, C2, 6. Okay, and I keep doing that. So for CK, this would consist of the union of all of the intervals that look like 0 to CK1, union CK2 to CK3, union, and I keep going. Okay, and how many did I end up getting? Let's go back up and take a peek. So for example, when I did C2, how many total endpoints do I get? Well, I have 4 intervals, but each interval gives me 2 endpoints. Now the 4 came from 2 squared, all right? And then down here, when I double again, I'll have 2 cubed intervals, but that means I get 2 to the 4th endpoints, because each interval has 2 endpoints. All right, so the total number of endpoints is going to be, for k, will be 2 to the k plus 1. So here I'm going to have ck, and I'd have 2 to the k plus 1, but then I eliminate like 0 and 1 on the end, so there's actually only, I subtract 2. It doesn't really matter here, I just want to get it precise. Okay, and then the very last one here is a 1. Okay, so that's what my CK is going to be. All right. Let's see, a little observation that we should make. We know that C, which is equal to the intersection over all CLs, say, or yeah, that's fine, L, L at least 0. This is contained in this CK. So every element in the Cantor set is contained in any one of the CKs. And so if I apply the characteristic function, or the indicator function, to some point x, this is going to be less than or equal to the indicator function on CK evaluated on x. So if it's not obvious what that means, the indicator function on CK of x, this is again 1 or 0. It's going to be 1 if x is in CK and 0 otherwise. Okay, so what's going on, right? Like if x is in the Cantor set, then it has to be in CK, and they're both going to be 1. If x is not in the Cantor set, then this indicator function will be 0, but it could still be in CK, so this is either going to be 0 or 1. And so this indicator function will always be at least as big as the indicator function on C. All right, so this is true for all x in the interval 0, 1. Okay, fine. If I want to talk about integrability, of course, I'm going to have to start looking at lower and upper sums. That means I need some partitions. So let's see, what if I had some partition of 0, 1, then, well, let's make a little observation. If I take the lower sum for chi c and evaluate it on this partition W. Well, first, because the value of the indicator function is always 0 or 1, I know that the lower sum is always going to be at least 0. No problem there. I also know that the lower sum is always bounded by the upper sum. Okay, that's not a problem. But because this chi c is always less than or equal to chi ck, then I know that the upper sum of chi c is going to be less than or equal to the upper sum of chi ck. Again, evaluated on this W. Okay, and that's again why, well, the upper sum, you remember, in general, the upper sum of a partition, okay, you have a sum, and then you have the supremum of f evaluated on the intervals times the length of the intervals. Well, if I replace f by a larger function, then the supremum can only get bigger. So that's why you get this last inequality. So what my goal is going to be is to find actually a sequence of partitions W, and each one of those partitions is actually going to change which CK I'm really looking at here. But because I know that for any CK, right, that the upper and lower sums for chi c are going to be bounded by it, that's not going to matter. But I'm going to show that I have a sequence of partitions where these upper sums are going to converge to 0. All right, so that's going to be the goal, is to show I can actually, right, get this to converge to 0, and then by the squeeze theorem, the upper and lower sums are going to have to converge to 0, at least on those different partitions. Okay, so if I'm going to do that, then if I want to build a sequence and I want things to converge to 0, here's what I'm going to do. For little n, some positive integer, I know that I can make the lengths of the intervals of these CKs small enough meaning, say, less than 1 over n. All I have to do is go out far enough, all right? I just have to go out far enough. So let's see, for n, a positive integer, there exists some k, and this k will depend on n, okay? So we'll call this k of n in the very first instance, but after that we'll just write it as k. So there exists some positive integer k of n such that the length of ck, which we know is 2/3 to the k, is going to be less than 1 over n. Okay, so I'm going to be able to get these things very small. Okay, now I want to compute an upper sum for C sub k, right? Or for the indicator function on C sub k. So let's talk about what's going to happen if I do that. Well, I need a partition, and so I'm going to kind of think about the most naive partition that I could write down. Okay, that's going to be important. So the most naive partition I can write down is I start at 0, and I just go right to the, I don't know, C sub k1. And then I jump across and I get to C sub k2 and C sub k3, jump across again, C sub k4, go to C sub k5, and I keep going forever and ever. Well, not really, because I stop at 1. Okay, so 1 would end up over here. Okay, now if I try to compute the value of the indicator function on any of the black lines, I know it'll be 1. If I do it on any of the empty spaces, it's going to be 0. Now, if I'm computing the supremum of the indicator function on an interval, and if it contains any of the black points, the supremum will then be 1. But what that means is if I just use these endpoints, CK1, CK2, etc., even when I look at the empty gaps, I get those endpoints in the interval, right? They're just sitting there on the end. And then when I evaluate the supremum, I'm going to get 1, whether I'm on the black line or whether I'm working on the intervals in the middle. But if I do that, then, okay, the supremum is always 1. And so my upper sum would just be, well, 1 times the length of all the intervals, right? Or the sum of all the lengths. And the sum of the lengths is just 1, right? That's the entire interval. And that would mean my upper sum would be 1, which is definitely not 0. And it's certainly not something getting close to 0. So what I have to do is enlarge these intervals just a little bit so that the gaps don't contain any of the black points. Okay, so that's what I'm going to do. I'm going to just extend this out by a little bit on each side. Okay, each of these intervals, I just extend it out a little bit. Okay, and now let me call this distance delta. Okay, so I just extend out by delta. All right, well, how big is delta going to be? Well, okay, I know that since I'm working in C sub k, each of these intervals, these subintervals has lengths 1/3 to the k. I don't want delta so big that these red parts intersect each other. So what I'm going to do is I'm going to set delta to be a third of the length of the interval. Okay, so this will be 1/3 to the k plus 1. Okay, that basically means I'm chopping up these empty bits into 3 equal size pieces. Okay, so delta is actually the size of the piece in the middle too. All right, so that means when I define this partition, I don't want to use the CKs themselves, but rather the CKs and then adjusted by delta. So I define a partition W, and it'll be indexed by this n. So I'm going to get a partition for each positive integer. And it's going to be, well, we always start at 0, and then I go to CK1, but I need to extend out a little bit, so I add delta. Okay, now note, this k, right, depends on n. So even though it doesn't look like there's an n here, right, this really does depend on n. Okay, then I hop across, and the next point is, well, it's not quite CK2. You have to do CK2, but go back by delta. So CK2, but then we subtract delta. And in fact, you can see, right, it's going to alternate on all of the odd indices, we're going to get a plus delta, and on all the even indices, we're going to get a minus delta. So the next one will be CK3 plus delta, and then we'll have CK4 minus delta. And we keep on going until we get to the end. At the end, we're going to have a CK, and then this was 2 to the k plus 1 minus 2. Since this is an even term, we're going to get minus delta, and then finally we finish at 1. All right. Now, if I go to compute the value of my indicator function on any of these pieces in the middle, okay, so all these empty ones. Now I know that the value of the function everywhere in there is 0. So that's where, let's see, that's where it goes from an odd to an even. Okay, so on something like here, 1 to 2, or from 3 to 4, right? Chi c is, or chi ck is always 0 on these. So when I compute my upper sum, I don't need to worry about those parts of the partition. Where I do get something is, for example, here from 0 to the C1, or anything from an even to an odd. Okay, that's going to give me something because now the supremum on this interval, well, I know sometimes I get 0, sometimes I get 1, but the supremum of chi ck is 1. Okay, so what that means is that the upper sum, so the chi ck upper sum of Wn, I'm going to get by adding up all of the, well, let's see, the supremums are 1, so you could just ignore those. You're just adding up all the lengths that you get. So what are the lengths that we're getting? Well, in the middle, which is kind of the typical case, you see all these lengths are a black line with 2 red lines surrounding it. Okay, so the typical length looks like black line, and then a little delta length line on the ends, right? So we have a delta and a delta. And this stuff in the middle, right, this is a 1/3 to the k. Now, actually, we know what delta is. We have it here. It's 1/3 to the k plus 1. So this is a 1/3 to the k plus 1. This over here is a 1/3 to the k plus 1. So in total, one of these lines is giving me 1/3 to the k plus 2 copies of 1/3 to the k plus 1. Now, there are some exceptions to this, okay? So on the left-hand side, you can see there's a black line and a red, and there is no corresponding left red part. And over here at the end, right, you'd have this black and a little delta red, and there is no right-hand delta. All right, but if all I'm worried about is putting some sort of an upper estimate on the upper sum, then I'm just going to assume that all of these are a little bit bigger than maybe they are, right? So just assume all of them have this 1 black line, 2 red line length. So then the upper sum would actually be less than, okay, because I'm definitely overestimating now, this number, right? This is the length. And then how many are there? Well, in CK, we determined there are 2 to the k different intervals. So this is going to be less than 2 to the k times 1/3 to the k plus twice 1/3 to the k plus 1. Okay, so remember, this is now the length of the intervals. And this 2 to the k is the number of intervals. All right, well, now we can just play a little bit of algebra. First, this 1/3 to the k plus 1, I could think of this as 1/3 to the k times 1/3. And so now I can factor a 1/3 out of these two sums, or sum ends, and when I pull it out, I can combine it with the 2 to the k, and I'll get 2/3 to the k, and on the inside I have 1 plus 2 times a third. But 2/3 to the k, we had done something. We had made k large enough so that 2/3 to the k was less than 1 over n. So down here, this is less than, well, let's see, 1 plus 2/3 is 5/3, so 5/3 times 1 over n. This is fantastic because I have just shown that my upper sum for this particular partition can be less than, well, it's a multiple of 1 over n, but that's good enough. It's a positive multiple. And so what this says is that the limit of these upper sums, all right, now I'm allowed to change my partition n, right? And remember, as n changes, this is k of n, right? So k of n is going to change as well. This limit is going to be 0, right? Because it's less than a positive multiple of 1 over n. So we've done it. We've shown that we can build a sequence of upper sums that converges to 0, And each one of those upper sums is at least as big as the upper sum for chi c, because this was true for any partition W, all right, and for any ck over here. So by the squeeze theorem, and this was why it was important that we had bounded from below by 0, by the squeeze theorem, the limit of the upper sum for chi c on this sequence of partitions is equal to 0, is equal to the limit of the lower sum of the sequence of partitions. And this gets us back to our previous video on the sequential characterization of integrability, which said that a function was integrable if and only if there was a sequence of partitions such that the difference of the limits of the upper sum, or the limit of the difference of the upper sum and the lower sum applied to that partition was 0. Well, we know that, in fact, individually, right, these limits are 0. So this implies that the limit of the difference, and here I can just use the dot notation, of the upper sum and the lower sum of chi c applied to this partition W is 0. And so by the sequential characterization of integrability, chi c is integrable. Wow, that's awesome. As a little extra footnote here, right? We also showed in the sequential characterization of integrability that when you know that the function is integrable, then the integral is precisely equal to the limit of the upper sum. And so in our case, we know the limit of the upper sum is 0. And so we know that actually that if we integrate the indicator function over 0 to 1, we get 0. Whew, what an amazing journey. Now there's a lot more that one can talk about with the Cantor function, but I think we've done enough for now. All right, we'll see you next time.